Edwin Olson, and I'm an assistant professor in the computer science department at the University of Michigan. This is a brief overview of some of my current research interests. My research areas can be divided into three basic areas. The first major area is feature-based navigation. My work is focused on dealing with sensor noise and ambiguity, and with building algorithms that scale well. I'm also interested in path planning, particularly in contexts where there are kinematic and dynamic constraints that must be obeyed. An exciting and emerging research area is incorporating learning. How can robots learn to behave by watching and interacting with humans? In 2004, we deployed a number of autonomous vehicles off the coast of Italy. Our goal was to evaluate an experimental synthetic aperture sonar system, but this sonar system caused a great deal of interference with our long baseline navigation system. You can see this interference in the plot in the lower left. In order for the vehicle to compute its position, this data needed to be filtered. We developed a general-purpose outlier rejection algorithm based on spectral graph partitioning that automatically identifies and rejects outliers. Our approach has two key advantages over previous work. It does not require a prior estimate of what the true value is, and it does not require large runs of similar observations. For example, our method is able to identify intermittent inliers from distant beacons. This is especially important in LBL applications, since we are generally starved for data. Ordinarily, the GPS coordinates of LBL beacons are carefully surveyed. Imagine instead a scenario where LBL beacons are carelessly thrown overboard or dropped from a plane. Can a robot successfully navigate with LBL beacons when the position of those beacons is unknown? This video demonstrates that we can. We're computing the path of the robot and the positions of the LBL beacons at the same time. As you can see, we do have the ground truth data available, so we can compare the results of our approach to that of a known baseline approach. As you can see, our method does just as well as the baseline approach, and with our method, LBL beacons can be deployed without that careful surveying. It's also interesting to note that this result was obtained using the very noisy data we saw on the previous slide. The central focus of my PhD work at MIT in 2008 was building maps from very large numbers of observations. The more observations we have, the slower these algorithms tend to run. This video shows a synthetic map building problem consisting over 5,000 observations. This algorithm, state-of-the-art only a few years ago, takes over a week of CPU time to compute a reasonable map. We proposed a new approach to map building that is orders of magnitude faster than the previous work. In this case, we're able to compute a good map in just under 2 seconds, about 300,000 times faster. When combining large numbers of noisy sensor observations together, there's another issue perhaps even more important than speed. Specifically, does the algorithm get the right answer? Surprisingly, most existing algorithms do a very poor job at computing the right answer in high-noise environments. Essentially, they get stuck in local minima. Our approach does better. This figure shows that at very low noise levels, both our method and the next best state-of-the-art method do well. But as the noise level increases along the x-axis, our algorithm computes the right answer much more frequently than other approaches. This robustness to noise allows us to use cheaper, lower power, and more stealthy sensors while operating in cluttered and noisy environments. Robots have a hard time recognizing places that they've seen before. This means that they have a hard time closing loops and have difficulty reacquiring targets. In this dataset, the robot is limited to seeing only the white circles. These circles all approximate the worst possible case for data association because they're identical. The question is, can we recognize places that we've seen before by using constellations of these features? As we see in this video, the answer is yes. On the bottom of the screen, we can see the historical path of the robot as a thick line. Every time that we're able to reacquire a place, the map snaps into alignment. As we come around this final large loop, our position error is substantial. We're a bit lost, but when we see some familiar features, we're able to resolve our position. In short, our algorithm can deal with enormous perceptual ambiguity with virtually zero false data associations. Changing subjects a little bit. I was a technical lead on MIT's DARPA Urban Challenge vehicle. I was principally responsible for the object detection and tracking systems. In this video, we're extracting objects in the world, associating detections of those objects over time, and computing velocities for those objects. Another key challenge in the DARPA Urban Challenge was determining where it was safe to drive. This video illustrates a terrain classification system that classifies terrain as either safe, green, unsafe, red, or belonging to the edge of the road, yellow. This video uses LiDAR data, but we are currently extending our approach to deal with camera data instead. Once we've collected all of this data about obstacles and terrain, we can pose a motion planning problem. How does the vehicle get from where it is now to where it wants to go? In this visualization, red corresponds to places that we cannot go, black corresponds to places that we are free to drive in, and shades of gray correspond to places that we can drive through, but that we'd prefer not to. These gray areas encode trade-offs in driving behavior. For example, it's better to take a little bit longer to get where we're going than to risk a near collision with another vehicle. This video shows our motion planner running during the DARPA Urban Challenge. This motion planner is based on the Rapidly Exploring Randomized Trees algorithm. We're able to guarantee that the paths we select obey both the kinematic and dynamic constraints of the vehicle. At the same time, we're selecting paths that have low cost. In other words, we're selecting paths that obey the rules of the road. Here's a motion planner for a quasi-humanoid robot. In this case, we're dealing with simulated obstacles and sensors. The human operator commands the robot to move to the blue cross. The robot then autonomously computes a plan that will allow the robot to get there. The interesting aspect here is that there are many possible paths that would be successful. Which path should the robot take? The preferences of the robot are again encoded in terms of those gray force fields. One of our ongoing research projects is to teach a robot what those preferences should be using inverse reinforcement learning. For example, a robot could watch humans walk around, avoiding collisions with obstacles and each other, and learn how humans make their decisions. This will lead to robots that make better decisions that are more human-like. We're also interested in human-robot interaction. In particular, how do we reduce the cognitive load on a human operator? On the left, we see a conventional robot interface for a packbot. The soldier must manipulate controllers with both of his hands and pay attention to information displayed on an LCD screen. This is not only cumbersome, but dangerous. It is impossible for the soldier to maintain an awareness of the activities going on around him. A key advantage of the autonomous technologies that we're developing is that the robots require less attention by their human operators. We are developing unobtrusive and cognitively lightweight interfaces, such as the iPhone interface on the right, that allow the human to be a partner with the robot, not its servant. I'd also like to quickly mention a number of my other research interests. One of these areas is computer vision. In addition to stereo vision, I'm interested in computing depth segmentation and absolute depth from monocular cameras, in addition to vision-based object identification and classification. I'm also interested in detecting unusual objects. While many researchers have built car detectors, pedestrian detectors, bicycle detectors, and so on, how would we detect a mattress, or a tree limb, or a box that fell out of the back of a truck? For safe autonomous operation, our robots must be able to recognize more than a handful of object classes. I believe that learning can be applied to improve almost all of the topics I've mentioned today. I'm particularly interested in inverse reinforcement learning. Specifically, how does a robot learn to behave like a human? And finally, long-term autonomy poses many additional challenges, including reliability, scalability, and the question of how do we manage these massive data sets that a long-lived robot can collect. If you have any questions about this presentation, please don't hesitate to contact me. Thank you.